different arithmetic instructions we have in 8085 microprocessor, and this is like addition, subtraction, etc. But we don't have any multiplication and division instructions in 8085 microprocessor. If you want to perform multiplication and division, then we have to use different way by which we can perform this kind of operation. First, I will try to explain the addition operation, that is add R, add M. Means any kind of arithmetic operations, I already discussed that every time we need accumulator. Means here the add R means the addition done between the content of accumulator and content of the register. So it register may be any general purpose register, it may be B, C, D, E or HL. So add M means the content of the memory that is specified by the HL register pair and with the content of the accumulator. So we can take an example here, the instruction add B. So the content of A is stored 47 and content of B is stored that is 51, and here the addition is completed and we are getting 98H. Here we don't have any carry, that's why the carry is 0, and here the no auxiliary carry is generated from D3 to D4 bits, so that's why here the auxiliary carry is also 0. And here the parity is 0 because we have odd numbers of ones, and the result is not showing the 0 result. So this is a non-zero result, so that's why the Z flag that will be set at, that will be 0. So these addition instructions for this with the register, it has this is basically 1 byte of instruction, and for this register addition with the register has a 1 machine cycle. To operate it we need 4 T states, and for this addition with the memory, the content of the memory, it need 2 machine cycles, and means we need 70 states to operate these instructions. Next is the ADC, that is addition with the carry, add register to the accumulator with the carry. So we can similarly we can add the content of the accumulator and the content of the register with the carry, and content of the accumulator and content of the memory with the carry. Now we can take an example. Here the content of the content of BC is 2498 and content of DE is 54A1H. Now we are actually trying to add 16-bit of data, 216-bit of data. First the lower byte that will be added means 98H and A1H. So here we are getting the results, that is 39H, and a carry is generated. If we use ADC here, then the carry that will be added with this higher order data, that is 24 and 54. So here 24H, 54H and 1 is the carry that is added, and the result will be 79H. So by this kind of arrangement we can use ADC instructions to add the carry with the accumulator and the register, or with the accumulator or the content of the memory. And this ADC is a 1 byte of instructions, and for the ADC with the register it will take a this has a 1 machine cycles, it will take a 40 state to complete the operation. And for the ADC M, it has 2 machine cycles. To operate it we need 70 states. Next is ADI, 8-bit data. So we can directly add 8-bit data with the content of the accumulator. So example like ADI 59H, here the content of the accumulator is 4H, and 59H is added with that data, and here we are getting A3H, and the results that will affected on the flag. So here the flag we are getting that non-zero value, that's why the Z flag is 0, and auxiliary carry is 1 because here a carry is generated in the D3 to D4, and no, here the parity is 1 because we are getting the even number of ones here, and the carry is 0 because no carry is generated. And to operate it, this is basically a 2 byte of instructions. To operate it, we need 2 machine cycles, means 70 steps we require to complete these instructions. Next is the ACI, that is the add immediate to accumulator with carry. Add immediate to accumulator with carry means the content of the accumulator and the 8-bit data and the carry that will be added, and we will get some result, and the flags will be affected for the results. Here the example is ACI 57H, the content of the accumulator is 26H and the carry is 1. So all are added and we are getting this data. So here we are getting a non-zero value, that's why the Z is equal to 0, auxiliary carry is not generated, parity is 1 due to the even parity, and here the no carry is generated, so that's why it is 0. So this operation ACI 8-bit data, this is a 2 byte of instructions, and to operate it we need 2 machine cycles, means we need 70 states to operate these instructions. Next is a DAD. DAD register pair, it may be any register pair, means it will add with itself the register content of the register pair, that will add itself, means the content of the register pair that will multiplied by the 2. We can take an example, that is add H. The content of HL pair is 0242H, and we have to add the same data with it. So 0242H, 0240H, and we are getting 0484H. So this is the operation by which we can add the register pair or multiply the register pair by 2. So this DAD instruction is a 1 byte of instructions, and it has a 3 machine cycles. To operate it we need 10 T steps. Next is a SUBR SUBM, means subtraction basically done from the content of C to content of A. So basically content of A to content of C. So basically this kind of arrangement is done in another way, where we can take an example for the sub C, means subtraction C, means the content of C we will make its 2's complement, and then we will add the content of accumulator with it, and the results we are getting, if the carry, that will be 1's complement we have to do, and the results we will get, that is the subtraction results. Means we have to first take the content of the register, and then we have to do its 2's complement, then we have to add with the content of the accumulator, and the results we are getting, the carry we have to do a 1's complement, and after that the results that we will get the subtraction results. And similarly here the effect of the flag will be there. So this is the subtraction, and this for this operation SUBR or M, this is basically a 1 byte of instructions, and to operate it we need for the SUBR we need 1 machine cycle, means we need 40 steps to complete the operation. Similarly SUBM we need 2 machine cycles to complete this operation, means we need 40 steps for this particular operation. Next is SBB, that is subtract source and borrow from accumulator, means here the operation is basically the the content of B. Now we can take an example, that is SBB. The content of B is say 3F. Then we have to add the borrow with it, and we will get 40H, and we will do the 2's complement of this particular data. Then we will get the 2's complements of 40H, and we have to add with the content of A. So the results we are getting, we have to do 1's complement of the carry, and then we will get the final result. So that is here the example is showing that first we have to add 1 with the content of B. 1 is basically borrow, and we have to do 2's complement of this particular data that we are getting from the addition, and the content of accumulator we have to add with this 2's complement data, and finally we will get a result, and the results carry, that will be 1's complement. We will get the results of the carry of this result, that will be 1's complement, and we will get the final results. And SBBR, basically these SBBR and SBBM is a 1 byte of instructions. To complete SBBR we need 1 machine cycles, means we need 4 T-steps to operate it. Similarly, SBBM we need 2 machine cycles to operate it, means we need 7 T-steps. 2 machine cycle and 7 T-steps required to operate this machine SBBM. Next, SUY 8-bit data means subtract immediate from the accumulator. Means we will subtract the data from the accumulator directly, means we will provide a direct immediate data. Means we can take an example, that is SUY 37H. So the 37H will do the 2's complements of 37H, and we will add the content of the accumulator, and the results we are getting, obviously 1's complement will be done, and the final result we will get, that is a 09H, and the flag that will be affected like previous one. So this is a 2 byte of instructions. To operate it we need 2 machine cycles, and means 7 T-states we require to operate these 2 machine cycles. Next, SBI 8-bit data, that is the subtract immediate from the accumulator with borrow. So example like SBI 25H, so we will add the borrow with the 8-bit data. Here the 8-bit data is 25H, then we have to add 1 with it, so that is the 26H, and we have to do 2's complement of this 26H, and then we have to add the content of the accumulator, that is 37H, and we will get a result. After that we have to do 1's complement of the carry, and finally we will get the final results. And obviously here also there will be some effect on the flag, and this is 2 byte of instructions. To operate it we need 2 machine cycles and as well as 7 T-states. Next is the INR, that is INR AR, INR M. INR R means the content of a register that will be incremented by 1. INR M means the content of the memory that will be incremented by 1. So basically the content of the memory means the address holds that is HL register pair, and the content of the HL register pair, that is the address, and this address actually hold a data, and that will be incremented by 1. So for this INR R, example like INR B, INR M, so INR R basically a 1 byte of instructions, or INR M is a 1 byte of instructions. To operate INR AR we need 1 machine cycles, means 4 T-states we required, but INR M we need 3 machine cycles, means we need 10 T-states to operate it. Next is the INX R, and INX R means the content of the register pair. INX RP basically the content of the register pair that will be incremented by 1. Means if the register pair holds a 16 bit of data, that will be incremented by 1. Example like INX H, if HL pair stores a 16 bit of data, that will be incremented by 1. So this is a 1 byte of instructions. To operate it, we need 1 machine cycles, and means 60 steps we require to operate it. So next instruction is DCR R, DCR M. So the content of the register, it may be a general purpose register, may be B, C, D, E or HL. So the content of the particular register that will be decremented by 1. DCR M means the content of the memory that is held by the HL pair, that will be decremented by 1. So example like DCR B, DCR M. The DCR B means the content of B, that will be decremented by 1. DCR M means the content of the address, that will be decremented by 1. So DCR R is a R or M, that is a 1 byte of instructions. To operate DCR R, we need 1 machine cycles, means 40 states. But for the DCR M, we need 3 machine cycles, means we need 10 T states to operate it. Next one is a DCXR, and that is basically it is a decrement operation, means the register pair contains data, 16 bit of data, that will be decremented by 1. So example like DCXH, if the HL pair holds a 16 bit of data, that will be decremented by 1. So this is also 1 byte of instructions. To operate it, we need 1 machine cycles and 60 steps. Next, DAA, that is a decimal adjust accumulator. We have 2 examples to we can understand by using this kind of example. So first example is add decimal 12 BCD to accumulator that contains 39 BCD. So after addition, we are getting 4B, and in the lower nibble data which is greater than 9, that's why if you want to adjust the decimal, then we have to add 9 to it, then we will get the data as 51. So this is the decimal adjustment done. And in next example, the add decimal 68 BCD to the accumulator that contains 85 BCD. So after addition, we are getting 153 BCD, means EDH, where the lower nibble and upper nibble both are greater than 9. So we have to add 66 with this result. So after that, we will get the BCD, decimal adjust results, that is 53, and it has a carry. So this is a way by which the decimal can be adjusted, and the instruction we are actually using DAA, and DAA is basically is a 1 byte of instructions. So these are the arithmetic instructions, and that I already discussed all the arithmetic instructions and its operation, and its machine cycles, its T states, and the byte of instructions. That's all. Thank you.